All right, year 11s, welcome to your first lesson of the part 2 of our matrices unit. So we've already gone through part 1 before the holidays. We're now into part 2, and we'll be starting from part 2 here, which is further applications of our matrices. So in this part of this unit, we'll be covering communication matrices, inverse matrices, and simultaneous linear equations. There will also be elements within each of these that you'll cover. Today's lesson, we're going to go through 8.6. Let's begin. So in the previous lessons we've done before, I've already spoken to you guys about this idea of matrices and how they're related to networks. So networks is a diagram that looks like this. It's got a bunch of dots and lines, but there are specific names for them. And I've mentioned them before, that the dots are called your vertices. One dot is called a vertex, and the line is referred to as an edge. Reading this, it says a directed network is a graph network where the edges have a direction represented by an arrow on the edge. So previously we'd seen network diagrams that look like this. Okay, I'll make this nice and neat for you. Where, if you remember last lesson, I mentioned that if you see a graph that looks like this, or a network graph that looks like this, and you don't see any arrows, then presume or assume that they are bidirectional, meaning that you can actually go one way, and then you can also go the other way. Okay, but now what we're going to look into is a graph or a network where you've got a direction or a directed network where the edges have only one direction. So there's certain things you need to know. Remember that the dots are referred to as vertices of a vertex, and the lines are called edges. From this sentence, given that an edge is directed from A to B, so if you have an edge that's going from A to B, see how it's only one direction, the vertex A is called the tail of the edge, and the vertex B is called the head of the edge. So just some terms you need to know. The tail end of the vertex, edge, right here, A is the tail end of it, and over here is the head of this edge, and B is the head of that vertex. Okay, so just understand that the arrow or the edge has a tail and a head. And you can see at the tail of it, you've got that vertex, which is A, and at the head of this edge, you've got B for the vertex. All right, let's move on. Directed networks can be represented by adjacency matrices. So like I said before, there is a relationship between a network and a matrix. Okay, so you can represent your networks as matrices, but so can you with directed networks. Given that the rows are the tails of the edges and the columns are the heads of the edges, then the row in I, column J, is the number of directed edges from vertex I to J. Basically, what this is saying is, if you remember back to our previous lesson, when you tend to read a matrix for a network graph, you're looking at it as if this was from and this was to. So you always start from here to there. Okay, so the rows refer to the colors, where the tails come from. Okay. And the columns refer to where the tails are heading to. So it's always from, then to. Okay, so that's what sort of this sentence is talking about. All right, so let's represent the following directed network using an adjacency matrix. I'm just going to make this a bit bigger for you guys. So here we're going to represent this network as a matrix. So remember, it's going to be from and to. All right, let's name this. So you've got 4 vertices, okay, as in 4 dots, meaning it's going to be a 4x4 matrix. So it's a square matrix. We'll call it P, Q, R, S. Same up here, P, Q, R, S. All right, so let's fill this in. From P to P, actually, one thing you need to be mindful of, again, remember, this is directed, which means that some of the arrows or some of the edges only go in one direction. Okay, so keep that in mind. So from P to P, I can see that there is a loop. That means there's 1. Okay, from P to Q, so P to Q, I see 1. Okay, I only see one path there, so 1. P to R. Now, is there a direct connection to R? Well, you can see that this line is, but the direction is not pointing towards R, which means that this is not a direct connection or a one-step direct connection to R. So P to R is 0. Same with P to S. Because of the way that this edge points, it's going that way. That means you can't go to S directly. Okay, so P to S is 0, 1 steps. Okay, let's go Q to P. So from Q to P. Q to P, I can see that there's an edge there, but again, looking at that direction, it can't go there directly. So it's not a one step, or there's no one step way to get there. So 0. Q to itself, well, there's no loops, so that's 0. Q to R, well, I see there is 1 direct connection from Q to R, so 1. And in Q to S, there is also 0. R to P, okay, I can see from R to P, there's actually 1 direct connection. Okay, one step direction. R to Q, well, there's an edge there, but again, that edge points only towards R. So R is the head and Q is the tail. It doesn't connect directly, so 0. R to itself is 0. Okay, there's no loop for R. R to S, you've got 1. S to P, okay, I can see you've got 1 there, and it's one direction only. S to Q, there's 0, none. S to R, there's none, although there is an edge that connects them. It's only one direction, or it's directed only towards S, not to R. So 0, and then S to itself is 0. All right, so there is our adjacency matrix. Notice how yesterday, if you remember back to our lesson, if you were there, that I asked you guys, what do you find interesting about this matrix? So I put these square matrices, I put a line down here. Some of you said it was mirrored, okay? And that's correct if these were bidirectional, okay? If you could go back and forth. But because these are only one direction, it's not going to be mirrored anymore. See how the numbers or the elements in here don't mirror each other? Okay, that's how we get non-mirrored matrices, non-mirrored adjacency matrices. All right, let's move on. So you heard me before talking about one step or only one direct path. Now we're going to look into multi-step adjacency matrices, so more than one step. So different vertices or different dots can be reached from via other paths or via other edges containing more than one directed edge. So you can actually get from one vertex to another, okay, using not just one step, but obviously 2 steps. What we've listed here are just your one-step connections. But now what we're going to get into is your 2-step, 3-step, and multiple step connections, okay? So an n-step matrix is the same. It's going to be a square matrix. That doesn't change. And also the number in row I, column J, counts the number of paths from vertex I to J, not to vertex J, containing exactly n number of directed edges. What that's saying is basically same as what it said here before. It's going to be from to, but now it's the multi-step matrix is telling us how many multi-steps are there. So whether it's 2 steps, 3 steps, or 4 steps from this vertex to the other vertex. Okay, and we'll see that in practice here. So if your normal matrix is just 1 step, so let's say that's your 1 step. M squared represents the 2-step matrix. M3 or M cubed represents the 3-step matrix, and so on and so forth. So basically, that power or that the indice just tells you the number of steps for that matrix. So if it was an M3, so it'll list out the number of 3-step connections or 3-step 3-step connections that network has for that specific vertex. All right, let's just go into some examples so we can figure it out. Now, really quickly, I'm just going to copy and paste this. So we have it with us as a bit of a reference here. So this is, remember, our one step. Oops. This here, remember, is our one-step connections. Okay, and now if you look at the next few questions here, we're going to look at the two steps, or figuring out the two steps and the three-step connections. Okay, so let's start with the two steps. So remember, with these matrices, it's still going to be a square matrix. That does not change. Okay, doesn't change. It's still going to be from and then to. Okay, but let's just list out all of the vertices: P, Q, R, S, P, Q, R, and S. And now we're going to list out, remember, the two-step matrices. Now this matrix is called, doesn't have a name, I'm just going to call it matrix M. M squared for two-step matrices or two-step connections. All right. So let's look at P to itself. Does it have any two-step connections to itself? Well, if I'm trying to get from P to P, okay, I have a loop here. Technically, the interesting thing about this loop is I can actually go through it twice, to P and back to itself. That's actually one two-step matrix for P to P. P to Q, okay, adhering to the rules of the lines or the edges from P to Q. Well, I've got one step there, but if I go down here, that's already two steps. That's not P to Q, okay. Also, I cannot go through these lines or these edges because they're only one directional. So from P to Q, there's actually nothing, no two steps. Okay, two-step meaning I have to cross two edges to get to Q. P to R, okay, well, let's look at P to R. To get from P to R, well, I can go this way, I can go this way. So from P to R, there's actually one two-step, okay? Two steps meaning I have to cross two edges or go through another vertex. P to S, well, again, I can try and use this, P to Q, and then P to Q to R, but that's two steps already. I haven't gotten to S. So from P to S, it's 0. All right, Q to P. Well, Q to P can't go that way because it's only directed to go towards Q. So I can go down here and then go up to P. There's one, okay. But is there another one? I don't think so. I can go down here again, go here, but then that's to S. So Q to P, there's only one. Q to itself, well, there's no loop to go back to Q to itself, so 0. Q to R, well, I have one step, but remember, I have to take two steps, cross two edges. So technically, if I'm going Q to R already, that's 1, and then I can go to S, or I can go to P, but I haven't ended up at R. So technically, from Q to R, there's 0. Okay, Q to S, okay, this should have one, because I can go from Q to R, and R to S, that's two steps, 1, 2. So there's one two-step path from Q to S. I don't think there's any other one for that. R to P, so if we go from R to P, I could go R, okay, I'm at P, but the cool thing is I can actually take that loop. Okay, so there's one, that's one already from R to P, but also I can go from R through to S and then to P. That's 2. So there's actually two-step matrices or two-step connections from R to P. Okay, R to Q. All right, let's look at that. I can go this way, that won't end up at Q, but I can actually go R to P, then P to Q. See, there's a two-step there. 1, 2. Okay, so that means from R to Q, there's 1. I don't think there's any other ones. R to itself, 0. There is no loop there that I can take, unlike P. R to S, okay, having a look at how R to S works, I can go from R to S via one step, but then I'm forced to go up to P. That's already two steps, so there's none there. Same with this way. Okay, so R to S, there's 0. S to P, okay, this was an interesting one. Again, I can go to P via one direction, but because there's a loop there, I can also take that loop, sorry, one step, I can take that loop to make it two steps. So there's one two-step from S to P. S to Q, okay? Let's look at S to Q. S to Q, well, technically there, I can go, well, that's one step. So that's one there. S to R, so that's one of the two steps. S to R, technically no, because of that direction there. So S to R, 0, and then S to itself is 0. Now I realized, because of this loop, I actually made one mistake with P to Q. Okay, P to Q actually has, okay, one two-step there, because I can go P to itself and then P to Q. Right, that's actually two steps. See that? So technically, P to Q also has one. That is my bad. Hopefully that didn't confuse anybody. Okay, so that's for your two-step. Now let's try a three-step. So three-step is more or less the same. It's just now you got to take 3 edges, or you got to go from one vertex to another via 3 edges. Now, this is where it does get a bit tricky, but just bear with me. If you want to fast forward, go for it. That's fine. P S P Q R S. Okay, and I'm going to call this M3 because it's the 3 steps. Oh, one thing I forgot, by the way. I forgot to answer this. Find a two-step matrix and then write down the two-step paths from R to P. Let's answer that. So from R to P, I see you've got two steps there. So to go from R to P, let's write down all of the paths from R to P. Use green for this. So if you go from R to P, you can go R, 1, 2. So that's one of them. So from R to P, you can go R to P to P. And remember, that works because of that loop that P has. And the other path that R to P has would be R to S to P. So R to S to P. Those are the two, as you can see, from R to P, you've got two steps. All right, now we do the 3 steps. This one's a bit trickier, but similar principle, okay? So from P to itself, well, again, look at that loop. Cool thing is you can go 1, 2, 3, okay? That's one 3-step, okay, so far. But interestingly, the tricky thing now is you can actually have more. So that's 1, but you can also go 1, 2, 3. Okay, there's another 3-step. So from P to itself, okay, you have to start at P and end at P. There's actually 2 of the 3-step paths. So 1, 2, 3. That's 1. 1, 2, 3. There's 2. So there's 2 of them. P to Q. All right, well, let's do this. You've got 1, 2, 3. Okay, so there's 1 there from P to Q. See if there's any other ones. I don't think there is, because you can go 1, 2, 3, but that's already 3. So P to Q, there should only be 1. P to R, well, you could go 1, 2, 3. There's 1. Could you go this way? Technically, no. So there's only 1 from P to R. P to S, okay, you could go 1, 2, 3. Okay, there's 1. Let's see if there's any other ways. 1, 2, 3. Technically, no, I don't think you can. Also, adhere to the rules of the line. So there's only 1 of them. 1, 2, 3. There's only 1. Okay, Q to P. All right, Q to P, you've got 1, 2, 3. There's 1 of them. So QRS, that's one path. You can also go Q to R up to P, then do a loop. That's 2. So I've got 2 3-stage I don't think there's any more, so I'll leave it at that. Okay, Q to itself. Well, interestingly now, you can do this, okay? Because if you go Q to R, R to P, P to Q, that's 1. So Q to itself, there's one 3-step pathway. I don't think there's any other ones that exist. So Q to itself, there's one. Q to R, okay, this one's tricky. Is it doable? Well, again, adhering to the rules, Q to R, R to P, P to Q, that's not going to work. You can try this way, 3, that won't work either. I think Q to R has none. Q to S, so over here. 1, 2, well that's a 2-step. I'm already at S, but there's no loop to make me go back because of the edges. Can't go down because of that, so Q to S is 0. Alright, well that's all for Q. Now R to P. So from R to P, well you can actually go 1, 2, 3. So that's 1. But you could also go R, S, and then loop. Okay, so that's 2 3-steps. 1, 2, 3. That's 1 3-step. You can go R to P and P, P. That's 2. So there's 2 3-steps from R to P. R to Q. Okay, tricky one. Could you do that? So you can go from R to P. Okay, but they can go to Q, but that won't work. However, if you go R to P and then do a loop at P, that's 2, 3. See that? I'll do it again. 1, 2, 3. There's a 3-step. 1, 2, 3. That's 1. But you could also go 1, 2, 3. See that? There's 2 ways. Okay, so there's 2 3-step paths from P to Q. Oh, sorry, R to Q. My bad. Let me fix that. All right, from R to itself. Okay, we'll see if that'll work. R to itself actually is doable. Okay, 1, 2, 3. That's 1. You could also go 1, 2. Nope, that won't work. 1, 2. Nope, that won't work. Okay, it looks like from R to itself, there's only 1. R to S. Okay. That's a tricky one. You could go 1, 2, 3, but I'm already back at R. R, 2, 3. Nope, that won't work. 1, 2, 3. None of them. Okay, so R to S, there's 0. S to P to S to P. 1. Use that loop. 1, 2, 3. That's 1 already. You could also go 1, 2. Nope, that won't work. So S to P. 1, 2, 3. I think there's only 1 for S to P. S to Q. Okay, here we go. 1, 2. I'm already at Q, so what I'll use is that loop. 1, 2, 3. There you go. 1, 2. Yeah, that's really all you can do. 1, 2, 3. So S to Q, there's only 1. S to R. Okay, let's see. 1, 2, 3. There's 1. 3-step. 1, 2. Yeah, I think there's only 1 3-step from S to R. And lastly, S to itself. Well, let's see if that's doable. I don't think it is. 1, 2. Nope. 1, 2. Nope. Okay. S to itself. 0. And then from the rest of the question, find a 3-step matrix, adjacency matrix, and write down the 3-step paths from Q to P. So from Q to P, what's the 3-step path there? Well, let's look at it. There's one of them. What are they? So from Q, I'm going to end up at P. So you've got 1, 2, 3. That's the only one I see. So that means that path is Q to R to P to P. Q to R to P to P. That's the only 3-step path for this matrix. All right, now you might be thinking that's very, very tedious. It's going to take a while to do. That is correct. It will take a while. But fear not, because this is all doable on your CAS. However, you need to actually start off with writing down the 1-step, okay, the 1-step path. for the network. So to do that, on my CAS, just going to restart, guys, sorry. While we wait, on my CAS, it's actually doable. Okay, and how is that doable? Well, remember, okay, back here, what I talked about with these are powers, these indices. So all you have to do is get a matrix, a square matrix. There's one there. Okay, name it whatever you want it, and then put it to the power of whatever, or however many paths, or 1, 2, or 3-step paths you want. So let's try that here. Has it worked yet? Nope. Okay, it's still loading, but it is definitely doable on your CAS. Okay, and we'll prove that. Hopefully I got the answers right here for the 2 steps, so M2, and the 3 steps, M3. Taking this time. Okay, here we go. So I'm in calculator, add calculator, go here. This is going to be a 4x4. Okay, 4x4 matrix. So let's go up here. What are my numbers? Oh, that's M2. I want my 1 step. So you can only do this by first writing down the 1-step connections. Okay, you got to start there. So I've got 1, 1, 0, 0, 0, 0, 1, 0, and then you've got 1, 0, 0, 1. You got 1, 0, 0, 0. Okay, you're gonna name this. Name this whatever you want. I'm gonna name it M. Okay, so every time I press matrix M on letter M, it gives me that matrix. So let's test whether or not we got these right. So to get the 2-step matrices, remember 2-step would just mean to the power of 2. So if you go M to the power of 2, you can get power of 2, or the shortcut is, if you're smart, squared right there. Okay, you've got 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 1, 2, 1, 1, 2, 1, 0, 0, 1, 1, 0, 0. Let's test that here. Did I get it right? Oops. Okay, so 3 ones on the top, 1, 0, 0, 1, 2, 1, 0, 0, 1, 1, 0. Cool. And to get M3, it's going to be the same process. So M to the power of 3. Power of 3. And there it is. Okay, so let's see if I got that right. Ooh, okay, looks like I may have missed some. Q to P. Okay, I've got here. Oh, the only one I'm missing, it looks like it's the Q to P. Well, let's double check that. Q to P, I've got 1, 2, 3. Okay, I did miss one. Down here, guys. Q, 1, 2, 3. Okay, so I'll fix that up. 2. Okay, so let's fix that. The other path from Q to P is Q, R, S, P. All right, that's a 3-step. So let's put that in here. Q, R. I'm sure some of you would have caught this. So that's good. All right, moving on to the last bit. So that's how we get the multi-step networks. But remember, you have to start off by doing the 1 step and then just in your calculator, which I think is a lot easier than doing it by hand because it does take a while. And like you saw with Torio, you might miss 1 or 2. Okay, just get the letter or the matrix or the original 1-step matrix, sorry, to M. So for example, this one, you can even do it this way, to the power of 2. There's my 2 steps. Okay, if I want to get it, oops, it's confusing now, but going back to M, right there, you can even do M to the power of 3. M to the power of 4, as much as you want, okay? But that's the easy way on your calc. Now, last part here is just some application questions and communication matrices and networks, more or less the same thing. But what this part is talking about is that a directed network and a adjacency matrix can be used to represent communication channels. So communications between different nodes or different signals or different points from one tower to another, for example. A directed edge from A to B indicates that A can directly send messages to B. Consider this following communication network. Write down a one-step communication matrix. All right. So let's do a one-step communication matrix for this. Same thing with the previous ones. Remember, this is 4 vertices. So you're going to have a 4x4. Okay, remember it's from to. So A, B, C, D, A, B, C, D. Let's put the elements in. So from A to itself, actually for part A, it just says one-step communication. So you're only going to go one step. All right, keep in mind as well, by the way, looking at the arrows here, these are bi-directional. Okay, so you can go 2 ways with these if you wanted to. Okay, so one-step communication, A to itself is 0, A to B, you've got 1, A to C, you've only got 1, A to D, okay, you've got 0. Okay, why is it 0? Well, again, look at the arrow. It's really small, but it's only pointing, or it's only got one direction, and that's towards A. So A to D is 0. Okay, B to A, you've got 1. Okay, it's a bi-directional. B to itself is 0. B to C, okay, you've got 0 because, again, it's only one direction. B to D, you've got 1. C to A, I can see 1. C to B, there's only 1. And C to C is 0. C to D, I only see 1. Okay, D to A, I see 1 going from D to A. Look at that, one direction. D to B, it's going to be 0. Okay, because look at that, you've only got a one direction that goes towards B. That only goes towards D, so it's not bi-directional. D to C is also 0. D to itself is 0. Okay. So part B, to whom can A directly send messages? So who can A just directly send a message to? So we're going from and then to. So if you look at that question, who can A directly send messages to? Well, A can send directly to B to C. That's it. All right, so for that one, B and C. Okay, question C. From whom can C directly receive a message? So from who can C get messages from? Well, if you look at this, if you look at C, okay, you can only get C can only get messages from A. So it's got nothing else from B, C, or D. So that means C can only get messages from A. Okay, hopefully that's all made sense, guys. And one more thing is you might get a question like this where it's got 2 steps. Okay, so just keep that in mind and how to get your 2-step matrices from here. But I believe that would be it. Now on to your questions for 8.6. Thank you.